A very good day to Dr. Muhalim. I'm Woon Zijian from Group 7 and we would like to present our assignment 1 for cryptographic engineering, which is the crypto system puzzle. The total time taken to solve this decoded message is about 4 hours. My group mates are Leon Poon Kin, So Kian Wei and Khaled Hussein Ahmed. This is the outline of our presentation. Doctor can have a look on it. Firstly, we will discuss the strategies used to solve the cryptograms and share the decoded message. This is a ciphertext, and the only clue we got is the source, which is from Woodrow Wilson. After decoded it, the plain text we got is when I give a man an office, I watch him carefully to see whether he is swelling or growing. Okay, so now let's talk about the strategies we use to solve the cryptograms. These are the strategies we use, which is frequency analysis, decoding partial words, validating longer phrases, final mapping, and decoding the message. The first strategy we use is the most common strategy, which is frequency analysis. We begin by analyzing the frequency of each letter in the cryptogram based on the letters provided in the cryptogram 7. The results are shown in the table here. The number of P is 10, A is 8, Z is 6, BSD 5 each, ENOQ 4 each, LWXY 3 each, and CFJV 1 each. Based on our research in English, the most frequent used letters are ETAO, INSH, RDL, and U respectively. By comparing these frequencies to standard English letter frequencies, the most frequent letters used in the ciphertext were P and A, which likely corresponded to high-frequency English letters like E or T. We hypothesized initial mappings as a table besides here. The second strategy is decoding the partial words. The cipher segment we have here is TZPBAE. Initially, we have partial mappings so that we know that the Z is corresponded to H, P is corresponded to E, B is corresponded to S, and A is corresponded to T, leaving us with an incomplete plaintext of unknown, HEST unknown. At this stage, we look closely at the possible meaningful words or phrases, and the likely plaintext emerges as a when I, suggesting that the T corresponds to the W and E corresponds to the I. With this insight, we revisit and adjust our earlier guesses to ensure the accuracy. We finalize our updated cipher mappings as shown in the table here. T maps to the W, Z to H, P to E, B to N, A to I, and E to G. By considering our initial assumptions using logical reasoning and context, we have successfully decoded this segment. Next, we will validate with longer phrases. The next cipher segment we have here is AFPSVS, and currently is partially translated to the I unknown E, O unknown O, which still doesn't fully make sense. However, using the context clues, the phrase is likely to read as I give a. Expanding on this context, give a man fits perfectly and logically. Therefore, we confirm the additional mappings. F is corresponded to V, S is corresponded to A, and V is corresponded to M. Then, our revised cipher to plaintext table here now clearly reflects these mappings. Ultimately, the cipher segment AFPSVS gives a man.
Hi, good afternoon. This is Richie. So, based on the previous strategy and step discussed by Zijian, so I'm going to touch about final mapping table, which is under section 1.4. And based on the decoding partial words, validating of the longer phrases, and grammar checking. So, our group have obtained the final mapping table as below, and you can refer to the table that we have over here. Thank you. Hi, so the next slide is about the decoding of the message. So based on the cipher, which is the source that obtained from Woodrow Wilson, we're able to decode the text based on the step and strategy that we have used. So the decoded message is: when I give a man an office, I watch him carefully to see whether he is swelling or growing. So the next slide is regarding the justification of the decoded message. So based on the source that we receive from the assignment, so upon the receiving of this decoded message, we also do the double checking from either primary source, secondary source, to ensure that the decoded message is actually from this Woodrow Wilson. So the primary source actually we got it from this Wilson, which is under this the new freedom, a call for this emancipation of this generous energy of people, New York, from New York, which is the one of the speech contain the original phrasing of this sentiment by this Wilson. And the other secondary resources that we have is actually from these Cooper books, which is page 187, that quote Wilson using the phrase during his 1912 presidential campaign speech. And also, we're trying to search for Google pertaining to the decoded message that we receive. So it's also confirmed by these exact codes that this code decoded message is actually from Woodrow Wilson as well.
Hi everyone, my name is Saw Kian Wei. I will be presenting the relevance of cryptograms and encryption in the context of information security. Here's what we'll cover in the following 4 slides. 1. Confidentiality and data protection. How encryption keeps secrets safe. 2. Historical evolution. A quick trip through time, from ancient ciphers to World War II code breakers. 3. Threat modeling. How hackers attack and how we stop them. 4. Relevance to information security. Why this matters to us. By the end, we'll see how puzzles from history are the building blocks of today's internet security. Let's dive in. Confidentiality and data protection. Let's start with keeping secrets safe. Imagine we have a secret code where we replace letters, like turning A into S. That's called a substitution cipher. Similar to how modern encryption works. For example, if we send a message like office, encryption scrambles it into something like NYYAXP, so hackers cannot read it. However, contextual clues within messages can be exploited. For instance, short words like A often correspond to common letters in cryptograms. Similarly, patterns in phrases may persist in encrypted data. As cybersecurity expert Stallings notes in 2021, strong encryption, such as Advanced Encryption Standard AES, employs multiple layers of complexity to thwart such attacks. This approach is crucial for securing sensitive data, from financial transactions to classified information. Modern encryption algorithms like AES use confusion and diffusion principles to scatter data relationships, making even predictable inputs look random. The lesson? Confidentiality isn't just about hiding data. It's about destroying patterns that attackers exploit. Historical evolution. History shows us that encryption is a battlefield. The Romans used the Caesar cipher, shifting letters by 3, but it was easy to crack. During World War II, the Germans used the Enigma machine, a fancy code machine with spinning rotors. But Allies broke it by noticing patterns, like how some letters appeared more often. As David Kahn explains in the Codebreakers 1996, this tactic revolutionized code breaking. Fast forward to today. Machine learning models now analyze contextual patterns to predict email content or crack weak encryption. The evolution from manual frequency analysis to AI-driven attacks underscores a critical truth. Encryption must keep pace with technology. Modern systems like RSA and AES don't just shuffle letters, that they harness prime numbers and bit-level chaos to stay ahead of these adaptive threats. Threat modeling. Attackers today are modern code breakers. They exploit patterns like frequency analysis in ciphers or predictable phrases in encrypted data. Consider Bruce Schneier's 2015 example, side-channel attacks on IoT devices. By analyzing power usage or timing, hackers infer encryption keys, just as solving NYYAXP as Office relies on contextual guesswork. The defense? Randomization. Sorting passwords, for instance, adds unique values to each hash, turning our password into something unreadable, rendering frequency analysis useless. Similarly, AES substitution, permutation network, scrambles data so thoroughly that even a single change bit alters the entire output. Relevance to information security. Cryptograms are more than puzzles. They're microcosms of cybersecurity. They teach us that security through obscurity fails. For example, a cipher code seems secure until we recognize it is not. Similarly, unvalidated encryption crumbles under modern attacks. Companies use tools like AES and RSA. They aren't just algorithms, they are being validated by experts to make sure they are unbreakable. RSA's reliance on prime factorization and AES bit-level chaos ensure that even AI-driven brute force attacks hit a wall. As Schneier warns, in an era of quantum computing and AI, robust encryption isn't optional. It's the bedrock of trust in everything from e-commerce to healthcare. In summary, the cryptogram serves as a blueprint for information security. It reveals how encryption logic works, how attackers think, and why we need systems built on mathematical rigor, not just secrecy. In cybersecurity, the past isn't just history, it's a playbook for building a safer future.
So, my name is Khalid Hussein Ahmed. My magic number is 244029. So, question 3. Uh, Emphasizing that the problem solving skills developed by us solving cryptograms are valuable in a field of cryptography. So, cryptographic skill development through a pattern organization. So, decoding the cryptograph development skills is critical for a cryptographic work. So first, a pattern recognitions. So we identify letters in frequencies, mirroring, and detecting vulnerabilities in encryption and algorithms. Iterative testing. So we trial errors and substitutions, resuming a brute force attack in order to debug the cryptograph code. Next is contractual logic. So in a fairing word like a very, so from a particular decryption in a key of side channel, analyzing where the attacks are in direct clue. So adjusting a map and parallels, updating encryption protocols when flagging functions. Now we come to an end. To conclude, we decoded message using a frequent analysis and pattern recognitions. These are same techniques from foundation to modern cryptography. So the core thing is that we can leverage is substitution by the sievers to reveal foundation principles and a modern encryptions like involving these concepts but uses a complex math itself. Skills we gained is a pattern recognition by detection weak keys in RSA, iterative testing by doing brute force strategies, and contractual logic by mitigating side channel attacks. That's all. Thanks.
That's all from us today. I hope Doctor enjoyed our presentation. Thank you.